Hi everyone, today we're tackling a triple integral problem that looks quite intimidating in Cartesian coordinates, but it can be elegant if we switch the perspective. We're looking at a region Q which is bounded by a sphere, a cone, and a vertical plane. Our goal is to evaluate this integral where the boundaries involve a sphere and a cone. Therefore, we're going to use spherical coordinates. It seems fit for this integral. First, let's visualize the domain Q. So the first equation, which is z equals to the square root of 16 minus x squared minus y squared, is the upper hemisphere of a sphere with the radius 4. The other equation is z equals to square root of x squared plus y squared. This equation defines a cone that opens upwards at a 45-degree angle. Finally, the constraint x is larger or equal to 0 just means we are only looking at the right side of this so-called ice cream cone. If you look at the projection onto the xy plane, we can see a semicircle. This is crucial because it tells us our rotation angle, or theta, only goes from negative pi over 2 to pi over 2, rather than a full circle. Now for the math, we can transform the equation when multiply, which can result in the equation rho to the power of 6, sine to the power of 3 phi, and cos to the power of 2 theta. Now, let's set up our equation in terms of limits. We've converted our variables and found the limits where the radius goes from 0 to 4, the angle from z-axis goes from 0 to pi over 4, and the rotation, or in this case theta, goes from negative pi over 2 to pi over 2. We're going to solve this as one continuous process, working from the inside out. So basically, we'll start by peeling the rho layer or radius layer, then moving on to the phi layer, and finally finishing with theta. This ensures we can keep the geometry of the region Q intact as we integrate, so nothing goes wrong. So, step 1, the inner layer. We focus only on the rho terms. Everything else, the sine, cube, phi, and the cos squared theta, act as a constant for now. So integrating rho to the power of 6 gives us rho to the power of 7 over 7. When we evaluate this from 0 to 4, we get a constant factor of 16,384 over 7. Now, the second step, the middle layer, phi. Now we bring that constant outside the phi integral. We are then left with the integral of sine to the power of 3 phi. To solve this, we use the identity sine squared phi equals to 1 minus cos squared phi by using a simple u substitution, where in this case u equals to cos phi. We can evaluate from 0 to pi over 4. This gives us the value in brackets 8 minus 5 times the square root of 2 close brackets over 12. We now multiply this by our previous result. Step 3, the outer layer. Finally, we reach the outermost layer. We have a big constant term from our previous steps, and we are left integrating cos squared theta from negative pi over 2 to pi over 2. Using the power reduction identity, we find this integral equals pi over 2. By keeping it in one nested flow, we can see how the volume grows from a point into a wedge and finally into the half cone shape defined by the problem. The final simplified answer, we get 2048 times pi times in brackets 8 minus 5 times the square root of 2 close brackets over 21, which equals to approximately 284.61. Now, the takeaway here is the problem looks very complex. However, if we choose the right coordinate system, it can allow us to decouple the variables and solve the problems instead of this one massive problem. Thanks for watching, and I hope this helps you visualize triple integrals more clearly. Thank you.